PM, okay, already, okay.
And then we'll check with
Tell Nirmalya. Yeah, tell Nirmalya. He will also see. My hope is the remaining classes I'll do representation theory of no of SUN, okay, up to SUN SON I will do, okay, enough to be able to do calculations, okay. Then we will decide later because the semester might be over, but the thing that you will be, if you do quantum field theory, it will be extremely useful is Poincare group, and if you want to go into the higher reaches of algebras also, but we will decide it as we go, depending on the interest and so on we will decide, okay. So what I did last time was, okay, let me see, I was trying to do Casimir's, right. I was doing Casimir invariance for Lie algebras, okay. Okay, and what we found was, if the Lie algebra, you have என்ன AC இல்லையா?
Total power cut
today. L is simple, okay. The Karta killing form GIG, which is trace of add, I think I called it LI, add LG, is non-degenerate. Okay. This we proved, Li being a basis for L. Say, it can be also semi-simple. If it is semi-simple, it simply blocks. So it is not a new result, okay. So this is a really a basic result. So from here, this implies G inverse, okay, this matrix exists. Inverse matrix exists, right. So from here, you could construct, gives quadratic Casimir operator, let me call it C2, which is G inverse Ij times Lij. So this is commuting with all the elements of the Lie algebra, so it becomes a multiple of the identity in any irreducible representation, okay. So it can be used to label the irreducible representation. What about higher Casimirs? Okay. For example, you can write a kth order Casimir as the following. This is a generalization of this trick here. So what you do is you take add of trace of add Li prime, add say let's write I1 prime, I2 prime, add Li k prime, okay. Then you multiply it by G inverse I1 prime I1, G inverse Ik prime Ik, okay, times, this is a bracket, times Li1 Lik, okay. This is commuting with all the elements of the Lie algebra for the same reason that this is commuting with all elements of the Lie algebra, because when I do a conjugation with an element of the group, it rotates this, but G inverse you can transfer it to the rotation to the I prime indices, so it will go here, but that will be a conjugation at the two ends, so trace will take care of the trace will remove it, okay. So these are the higher Casimis, okay, which you can write down, but not all of them are independent, that is it will terminate, we will see how it goes, not all are invariant, are independent. I will come back to which of them will be invariant, how many invariant Casimis there are, okay. Invariant means fixing two of them should not fix all the remaining ones, the third one should not be an algebraic function of the previous ones, okay. So there are theorems on who is somebody is coming, okay, okay.
Wait, by invariant you mean independent?
Huh?
By invariant you mean independent Casim?
These are the independent means the following, if you have a relation like suppose you have C1 up to CL and suppose all the higher ones, okay, are, so there is some function of this which will identically vanish, identically, okay. Whereas, so you must have in all representations, so it will vanish in all representations, okay. So that means that the value of this operator in any representation can be computed from the values there, so it is not an independent label, okay, right. So the vanishing of this such a existence of such a relationship between the Casimis means that some other things you are putting in are redundant, they can be determined by the remaining ones, okay. So they are not algebraically independent, okay. Okay, so in this connection, since I have said this, let me spend a minute on the rank of Lie algebra. Again, an important concept. Okay. The rank is, okay, the notation normally people use is let H contain L be the maximal abelian subalgebra. I will give you immediately examples. Okay. It is called, it is a Karthal subalgebra, it is the so called Karthal subalgebra. It is a basic theorem that it is unique up to conjugations by the group let me call it G generated by L. By exponentiation, okay. That is H going to G H G inverse. G is in G. So G, you are given the Lie algebra. So by exponentiating and producting, I get a group. Okay, this is your universal covering group. That will act on H by conjugation, because you can expand this in multiple commutators and use Lie algebra relations. So this will map H to another H, which will have the similar properties. This uncertainty is always there, but modulo this H is unique. Okay. This H here, H is the analog of the complete computing set. Of Dirac. In quantum mechanics, okay, you have for the state labeling, or when you make observations, you have the concept of the maximal number of operators you can see. Okay, it's called the complete computing set. It is the exact analog of that here. Okay, the group H generates the group. Okay, it's called T in G, generated by H. Okay, is abelian. Because and is called when G is compact. Okay, T is called the maximal torus. Okay, it is a name. Okay, it is abelian. Is some U1 cross U1. Otherwise, you get some R's, real lines. Okay, this again is a result in Hamilton-Jacobi theory. If you know Hamilton-Jacobi, you have studied. If you go to what they call Lagrangians, you know the phrase Lagrangian submanifold. You know it? Okay. There you get, yes. That's where the PDQ, dPdQ vanishes.
Okay, yeah. Oh, right.
Lagrangian submanifold is where dPdQ, if you put it on the surface, vanishes. Okay. There that topology of that object, okay, is completely controlled by this kind of by vector fields which are just abelian. They commute with each other. Okay, and is called so that is the exact analog of what happens here. Okay, if you quantize this, if you are in the context of quantum theory, this will of the group G, you will find this as the Lagrangian submanifold, appropriately understood. Okay. This plays a very important role Okay. In non-abelian monopole theory. Please check about this. I am still thinking. Please check with Ramanujam. If he is not coming, then I am thinking that maybe you can even shift it in the morning, okay, if it is convenient. So it's okay with me in the afternoon. Then we can meet somewhere, we two, and we have to tell Rajavardhan. Okay, huh? We should inform him, but I am free in the morning. 11 o'clock afterwards, I have no problem. Okay, 11 to 12 can be. Or, yeah, 11 to 12 is good. Okay, so check with him. Okay, huh? Then probably which room is vacant, you have to look in the. That may be every.
The rooms like 117 will be free.
117. Yeah. Where is that?
First floor.
Yeah. Is vacant, so we can meet in 117. Parvalilla. Huh? Free so you check.
Check with them and I'll write you.
Yeah, find out and say, let me know. But if there is a problem, we can keep it here. So just let me know. We have only 3-4 classes, so I would prefer not to miss classes. Okay? So I feel I have done a rounded job. Okay. 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 This is very important. For example, in the non-abelian monopole theory, it has played a these are the BPS states. In the string people, Bogolyubov, Prasad Sommerfeld states. So this thing comes in a heavy way. It's all kinds of mathematics comes here.
So non-abelian monopoles, are they generalizations of Dirac monopoles to?
Sorry?
Non-abelian monopoles are generalizations of the Dirac monopole to?
They are Dirac transition functions. Okay, this let me finish this. This is yeah. You see, the Dirac monopole is on a sphere. The transition function is valued in U1. Okay, it's a closed curve. I mean, we have seen. Well, if you know the theory of transition functions, it's a U1 bundle, which is related. Here, the transition function between two patches is valued in a non-abelian group. Okay, so it is a different different situation. Okay, and that causes all kinds of new features. Okay, so what is it called? Langlands. Some strange thing in mathematics. Langlands duality or GNS, Goddard-Neutz or GNO duality. All these things get connected. Okay, Langlands thing is very complicated. I don't understand. Okay, it's something part of a Langlands program which I don't understand. But this paper is very readable. GNO, Goddard-Neutz Olive, and they discuss how this happens. Okay, and it is very beautiful. Okay. But anyway, let us keep going. Let me give you examples. Okay. So the rank. Okay. The rank of L is equal to dimension of H, dimension of the Karthasov algebra. Okay. And it is a theorem, not easy to prove, Raka. Number of independent Casimies is equal to rank of L. This is not a, I have not seen, well I think I have seen it, but it is so long ago. Raka gave some lectures in Rome, I don't know, somewhere, okay, where he described the proof. Okay. This is so long ago, I don't know how he did it, but probably we can reconstruct what we need, but I have not thought about it recently. Okay. But it is a fact. So let me look at SU2 example. Rank is, well, H is span of minus I sigma 3 over 2. This I mean that you take all complex multiples of this. So rank is, or it could be any other thing, any conjugation. So rank is 1. Okay. So there is only one quadratic, only one Casimir. C2, which we wrote, no? We will work it out. If you, it is simply minus, okay. Well, the way I wrote it is simply Li squared. Okay. If in basis, I will come to that in a minute. In basis where Gij is delta Aj. The Casimir is, so for example it could be the square of the sigmas, okay, sigma over 2, so you will get 3/4 and so forth. No? So this is L plus 1. So this thing C2 is what we would call normally, say, J squared, but J is angular momentum. This is another notation. Okay. If you take SU3, here remember the basis, okay, B alpha beta, B rho sigma, I wrote this, no, is delta alpha sigma, B rho beta minus delta beta rho, B alpha sigma. These are the commutation relations, where the B's are the tensor generators and B lambda lambda was 0, right. So the H is spanned by, okay, so it is simply span of, that's right, C of B11 B22, because when I take the commutator I get delta 1 2 which is 0, okay. Okay. So it is just 2 dimensional, so rank is 2. B33 is fixed by B11 and B22 by this equation. So the Casimirs, there are 2 Casimirs. One is C2, which is B rho sigma, B sigma rho. The second one is C3, which is say B rho sigma, B sigma tau, B tau rho. The rest are dependent on the previous ones, but if you try C4 can be expressed in terms of C2 C3, but the way you reduce is not trivial, and this was first explicitly shown by Okubo, okay, that I know. Okay. Theorems are all right. If you do calculations, you would like to know how to manipulate things, okay, and he was the first one to do this, okay, that I know. Okay. Okay.
You said higher Casimirs depend on these two.
Yeah.
The existence of higher Casimirs, like,
Sorry?
do higher Casimir operators always exist? You have
For Casimir operators exist only for simple and semi-simple algebras.
yeah, but once you have that, do you have a whole?
But you can write them down, but they won't be independent. You can simply take square of 1. Okay. This thing, for example, this thing here, fourth one, it will become some expression involving squares of b's in various combinations. C2 in some various combinations. Okay. Some all kinds of combinations come, which I am not remembering. Okay. This formula was very important when Okubo proved the so-called Gelman-Okubo formula for the elementary at the octet of elementary particles, okay, which was then quickly experimentally verified. Okay. It led to the discovery of the omega minus, which was the first hint that not first hint, which was over strong confirmation of the then emergent model of of elementary particles, okay, of quarks and so forth. It was emerging, okay, and this was the first very clear affirmation that what people were guessing is in fact correct. So, and that formula played a very important historical role. Okay. So, yeah. Okay, now, by the way, I want to also to give, okay, try again these problems. With this I stop. 43, 45, 46. Now, I want to prove, okay, one more useful thing before I summarize representation theory of SU2. Okay. And what I want to prove is the following. To prove if the Lie group G is compact, okay, there exists a basis where, okay, there exists a basis where, okay, this object here, let me call that basis L hat I of L of the Lie where, okay, this object here Gij, which is trace of add L hat I times add L hat J. I am changing the basis. Is equal to some constant, constant times delta Ij. A very useful thing indeed. So, how do I prove this? Well, it goes yeah, indeed, okay. You can do better, okay. In any IRR gamma of L, this object trace of gamma L hat I, gamma L hat J is equal to k gamma times delta ij. Okay. So there is an orthonormal basis. What it shows is that if G is compact, like SU2, SU3 and so on, the Lie algebra admits an orthonormal basis. It is really like a flat, Lie algebra behaves like a flat Euclidean space. Now how do I prove this? Well,
Is that I mean, I would think that would be true, right? Because the Lie algebra is like from the Lie algebra you get the Lie group. Lie group may be some complicated manifold.
huh?
From the Lie group can be some complicated manifold.
Yes.
Lie algebra is a small.
Yes, the tangent space.
Yeah. So it's relatively simple.
But for example, there is no, if the Lie algebra, the G is not compact, okay. For example, SL2C or SL2R, the tangent space, the Lie algebra is simple, so it has a non-degenerate metric, but the metric will not be, it will have signature, it will have certain number of plus and certain number of minus signs. Okay. The invariant metric that we are finding, this object, will be pseudo Hermitian, that is, what is it called? It will be Lorentzian with some signatures. Okay. For the Euclidean groups, for the compact case, it is in fact delta 1. So this is a very striking result, and it has been used. Okay. Why am I? So in this basis, okay, this object C Kij, okay, is totally antisymmetric. Let me call it C hat Kij, where L hat I, L hat j is C hat K I j L hat k. Okay. So in this particular basis, this C hat looks like a Levi-Civita symbol on the group, on the tangent space, okay? And this result is very important. Okay, in discussions of anomalies. Within quotes, in quantum field theory. When people initially found anomaly means classical groups can become, something can go wrong when you go into quantum theory. It may become, they may become non-implementable in quantum theory. Well, okay. The basic reason that happens, okay, this is a field where, this anomaly field is where operator theory inevitably gets mixed up with symmetry considerations of a classical type. What happens is that you probably have heard, or maybe heard murmur or rumor, that things like Hamiltonian, which is 1 over 2m times minus Laplace squared, it's an object like this, okay, is supposed to be an operator on some Hilbert space, for example L2 of R3, right, this operator. But this operator is not defined in all of this Hilbert space, cannot be, obviously because there are twice differential here, whereas the Hilbert space consists of all possible functions, okay, which are, only requirement is that they are square integrable, okay. So there are all kinds of discontinuous functions, they are in fact equivalent classes of Lebesgue square integrable functions. Okay. So this operator is not defined in all of it, but only on a subset of this, which is called the domain of this operator. Okay. Only in that domain does this operator make sense. Okay. And that has to be carefully specified in many cases. What happens is, for a classical symmetry is, can happen is that the classical symmetry acting on the domain of the Hamiltonian may take you out of this domain. Okay. When it does that, when it happens, that the operator is not compatible with time evolution. Exactly. So you find that what you thought was a conserved charge is not conserved. This happens for axial anomaly in quantum, so-called axial anomaly, which is standard in QCD. Okay. And then people found that similar anomalies were plaguing weak interactions. When people were trying to set up weak interaction theory, they came across many groups which they wanted to gauge, and they were having this problem. Okay. They did not put it in this language, but when they did calculations, something was going wrong. Okay. So people wanted to know what are the anomaly free groups, because only they are candidates for describing elementary particles as gauge series, and in that context this result played an important role in classification of anomaly free groups. Okay. And you will see old papers where this discussion is carefully carried out. Okay. So how do I prove this? Well, the proof is the following. Okay. Let me call it D S be the matrix in the adjoint representation in basis Li in some basis. Choose some basis. Okay. Okay. And I am assuming that the G is compact. Okay. So this is we assume G, or rather G0 is compact. The kinetic component of G is compact. That is all that is relevant in this case. Okay. Then we know, so this is ds is a representation. So what I got is ds in the adjoint representation, add Li, ds inverse is add Lj times ds ji. Right? This is a matrix for the adjoint action of the group element acting on the Lie algebra, and I choose some basis. Okay. Now clearly ds is real. As L is real. L is a real Lie algebra. Now we know from general theory that there exists a basis where ds is unitary. Okay. That is, we know that in basis, let me write the basis as L hat I, okay, and that is equal to, let me get the factors right. Yeah, integration on G0 d mu of s script ds dagger script ds to the minus half, okay, j I l j. So this is a new basis, yeah, L hat I, where this is a basis C lecture, C finite group lectures, not finite, C old lectures, where I wrote this integral as sum, okay, where the matrix ds becomes orthogonal. Or do let us say unitary. What do I mean by that? I mean that if I take ds L hat I ds inverse is L hat j, now the matrix will change, d hat of j I of S, and this is unitary, because I showed that you can always make a similarity transformation for a compact case, for everything becomes finite case, which is also the compact case where everything becomes unitary, but this d hat is still real, is still real, okay, as this matrix, okay, this object here, let me put it like this, 1, as 1 is real, because this is real, so it is real and unitary, so it is real and orthogonal, right? I mean it is real and unitary, so it is orthogonal. So d hat S, okay, is orthogonal and real. Yes. Okay. So is this object exponential t, okay, since let us write it d hat, okay, of what to write, d hat of an element like Li, okay, no t, okay, t, where this thing here is so what I am trying to do is, in this basis this is real orthogonal, so I am looking for the corresponding Lie algebra elements. Let me get the notation right, is L hat I think. Let me write like this, not let me write it correctly. So is add L hat I, okay, in this basis, okay, that is I look at add L hat I, where this is defined by acting on L hat j, okay, this is L hat k, okay, then I had dk, let me have dk high L hat j, you see this is of add L hat I, this j. Okay. I am looking at, I got this is a matrix in a particular basis of the Lie algebra elements. I compute the corresponding Lie algebra element, okay, in that particular element of this particular basis in its own basis. So I take the element of this basis, special basis, and see what this matrix is. This is matrix. And what I am telling you is, with this definition, this is real orthogonal. So this is, so this matrix here, d hat of add L hat I don't need to add here, that is what is confusing me. Yeah, I don't need to add here. D hat of L hat I is what? Real antisymmetric. Let me check again, okay. I got this matrix, this is an element of the group, okay. This is a real orthogonal. Now it is a matrix, so it depends on the basis. But now therefore I look at the particular basis which led to this expression serving as a basis for the action of the adjoint representation. I take the elements of that basis, which is this, okay. And how is this defined? It is defined by this equation here. So this matrix I am getting out for this particular basis in the abstract Lie algebra, this is adjoint representation of this one, okay. If you want is the matrix, so I don't write add here, this is real antisymmetric because this is real orthogonal. So what does it mean? But right hand side is equal to L hat I, L hat j, right. Which by definition let me call it C hat k I j L hat k by definition. But this is now I am telling, okay, is antisymmetric in by this equation in kj, these two indices. That is what this says. So it is by this equation, but it is already in Ij also, clearly also in Ij, okay. So it is totally antisymmetric. Okay. The existence of this totally antisymmetric this structure constants is necessary and sufficient for the Lie group to be compact. Okay. Now let me look at the following thing. Trace of gamma of L hat I, gamma of L hat j. Okay. So I look at this form here. I mean, L hat is a special basis, and I write it down, and I want to understand what happens with this. Okay. Now I take the element of the group. Okay. Let me call it what I call DFS gamma L hat I, DFS inverse, DFS gamma L hat j, DFS inverse is in some representation. Okay. Gamma is some representation, this is exponentiated representation, and this equation is true. But then this one conjugating it will be the matrix of d hat in this special basis. So it will be what? Ji of s, okay, d hat of ji, this I shouldn't write here j, ki, I should write here lj script of s times trace of gamma of k gamma of l, where here this is group element but is actually by conjugation. So I look at the matrix of D in this basis, that is by definition this, okay. But this is real orthogonal. So this says this by as d hat of S real orthogonal. What do I say? I find that this object here, some index, yeah, this object here, okay, this matrix gamma I gamma j, okay, as a matrix commutes with d hat of S. I have not made any mistakes, you know. Yes, because this is this matrix. Let me look at the index. This is symmetric. So you get. I am looking at the index. Yeah. Yeah, sure. This one is inverse. So this is the same as this matrix d hat inverse this matrix d hat. So you can pull this. D hat ik, this is d hat ik, you can flip the index and put the inverse, okay. This is real orthogonal, okay. So you can take the adjoint and which is the inverse, okay. So it will become d hat inverse this matrix d hat is the same thing, so you get this. What does it mean? If the gamma is irreducible, if gamma is irreducible, it says trace of gamma of L hat I gamma of L hat j is k of gamma delta ij by sure. Okay. So by sure, so there is a special basis with which we can diagonalize the Cartan-Killing form with eigenvalues only all equal. In fact, we can actually evaluate this. Okay. We can find what is k gamma. That will be my last k gamma. What do I do? Set I equal to j sum. Then as G inverse Ij is proportional to delta Ij, this object here gamma L hat I is quadratic Casimir up to normalization. Right? Yes. So because otherwise I would have put a G inverse, but G is 1. Okay. So this is equal to some quadratic Casimir in the representation gamma times unit matrix. So I put it here. This trace is happening in the. This is a trace in the representation gamma. Okay. So if gamma is dimension of gamma, there is no I here. the trace is in the representation gamma, the left hand side C2 gamma from here, trace of 1 is gamma is equal to the right hand side, which is k gamma times, I am summing over I and j, so is the dimension of the Lie group, okay, times dimension of L, or we know what is k gamma. This is quadratic Casimir in the representation gamma, gamma divided by dimension of the Lie algebra or the Lie group, whatever. So the normalization is fixed. Okay. So you can check this equation. Okay. Check it in simple case. I will leave it to you. Check for SU2. So what you are finding is this very elegant result, that there is a special basis which lets you diagonalize the Carthageal Lie form for compact Lie groups. Okay. And this is not just a formal result, because the existence of this basis means that the structure constants can be made totally antisymmetric, and this fact that they become totally antisymmetric plays a very important role in quantum field theory, because basically this total antisymmetry means that if you symmetrize, say for Bose particles, I mean there are diagrams where the C occurs, okay, and you have two photons coming out, but the photons are bosons, so if you symmetrize them, this kind of contribution will go to 0, okay, and that is how the anomalies get cancelled, okay, anomalies disappear, okay. So it actually has a significant role in the context of quantum field theory, okay. So tomorrow I will do this review. Just one thing, I will show you why the SU2 representations for angular momentum J are irreducible, because you have already done the representation theory. Then I will directly go into discussion of how to find representations of GLN, JLN, SUN and so on, okay, which will be my last set of representation theory talks for semi-simple groups. Then I will, depending on time, we will do Poincare. I think I will stop here and let me know what happens. Send me an email, but make sure, I mean, let there be no confusion, and let Rajavardhan also know, copy him also, okay.